Hopefully, we are all doing well today. Moving along with AP Chemistry, today we're going to be going over chemical bonding. So, first off, before we get started, please make sure you've got your notes and you are ready to kind of dive on into this with me. So, chemical bonding, what is it? Well, it is what it sounds like. It is where chemicals, elements, bond with one another. All right. In that, we're going to have a couple different types of bonds. We're going to have some ionic, some covalent, and some metallic bonds that we have formed. Sometimes there's a little bit of everything that's actually happening. But in this, we do need to know a little bit about what's going on the inside. Why is this actually going to be occurring? So, why does it occur? Well, first off, it occurs based off of distance and based off of the energy that they've got. So, for example, this is an example of a hydrogen bonding with another hydrogen. Okay, so this is how that diatomic hydrogen actually forms. So when you look at this, what you're going to see is that right here, in the grand scheme of things, we've got energy that's fairly high in comparison, right? Whereas down here, the energy is very low. Well, this is actually where your bond forms. Okay, so why does my bond form there and not up here where it says it's 0? Okay, or why doesn't it form somewhere over here or here? Well, when we're talking about these, we're going to be looking at those attractive and repulsive forces that we see in a molecule. All right, so let's talk about the hydrogen. Hydrogen has one proton and one electron, right? So if I've got these two protons and they're kind of moving along and they get closer and closer and closer and closer and closer until eventually they're right beside each other. What's going to happen when those two positively charged atoms get right beside each other? Well, what happens when you have two things that are positive, two positive ends to a magnet, and you get them close together? They repulse. So what we see here on this is we're going to see that that energy is going to get very high as we get those molecules or those atoms closer together. Okay. Now, let's say I've got, for instance, over here. Well, over here, if you notice, the energy is essentially the same. So why is it the same? Well, now, instead of getting really close, we're getting really far away. What happens when you get two magnets? Say they've got opposite charges, you get them far away. Do they attract each other? There might be some very, very minor attraction, but in the grand scheme of things, it's not enough to actually make them move, right? So what happens when we get them to that perfect distance, where they're close enough that there's going to be some attraction, but there's not going to be so much attraction that they're trying to slam into each other? Okay, because what happens when they would slam into each other? Now we've got that repulsive force that's occurring again, and so they're going to slowly start to move away. So they're going to move away. So I've got these protons, and let's kind of recap this. As they get closer together, get closer and closer and closer, what happens to my energy? My energy is going to become more positive. It's going to take more energy. Why? Because there's more and more and more repulsion the closer those get, more and more positives. Right there at this low point, which would be what we call our bond length, that's going to be the ideal place. That's where you've got an equal amount of attraction and repulsion that's going, and so you're going to actually form a bond between those things. And then as we move further and further and further away, what happens? Well, again, we're going to get so far away, our energy is not enough to hold those things together. So bonds form, for a bond to form, it has to be in an ideal condition. Right? It has to be the perfect distance away with the right amount of energy. So let's actually look at that. So Coulomb's law kind of addresses why this occurs and how it occurs and how much energy is actually there. And if you've taken physics in the past, or if you're currently taking it, y'all will actually talk about or have talked about Coulomb's law. Now, in chemistry, we need to know more about the concept rather than the actual math that's involved. You're not going to be asked to solve for Coulomb's law. You're not going to be asked to solve for the amount of force inside of it. That's a physics thing. In chemistry, we need to know it conceptually. What does it actually mean? Okay, so let's look at this formula. So here we've got our formula, and we've got force equals the charge of 1 times the charge of 2, so the charge of the first atom times the charge of the second atom, divided by their distance squared. Okay, well, we square the distance because there's two things there, right? So we've got these things. Really, in terms of chemistry, we can simplify this. The force equals our charge divided by our distance. So what does that mean? How do I conceptualize this? Well, the attractive forces between two charged particles is blank proportional to the magnitude of the charges. So let's think about this. If I've got a charge, okay, and let's say I increase the charge. So if I increase my numerator, what's going to happen to my force? Well, my force is also going to increase, right? So you increase the numerator, you increase the charge, you're also going to be increasing your force. Well, what happens? What do we call that when both things go up? We call that directly proportional. Okay. Well, what about distance? Okay. Well, distance is our denominator here. So if I increase my denominator, increase my distance, make the number that I am dividing by larger, what happens to my force? Well, the force is going to go down. So as I get further and further and further away, those attractive forces are going to decrease. Okay? So we call this an inverse proportion or inversely proportional. All right? Okay, so now we've got an idea about what's going on with our attractive forces, with the distance and the charge, and how that actually affects whether or not a bond will form. So let's talk about that bond forming. Well, bonds form with the electrons. All those types of reactions are going to happen inside of our electron cloud. And when we're looking at that bond that forms, stable compounds are going to have usually a noble gas configuration. So they're usually going to be looking at trying to get that full valence shell. Covalent compounds, which would be two nonmetals, right? That's going to happen by sharing those electrons. So they're going to gain those valence electrons by sharing them in between them. Ionic compounds, which is between a metal and a nonmetal, that's going to form when we see those electrons pulled closer to one side over the other. So we actually have an ion or a charge that forms because those electrons are pulled closer to one side over the other. Some examples of ions that can form would be sodium has a +1 charge because it's more likely to lose that electron because that attractive force between its electron is lower than the Zeph, the effective nuclear charge that's going to be pulling it from another substance. Okay. Some examples of elements with some set charges. Okay. These would be exceptions to our normal metals, right? Because our normal metals, when we typically think of them, group 1 typically has a +1 charge. Group 2 typically has a +2 charge. We skip our transition metals because the transition metals are very different in how they act, and so their charges can kind of be all over the place. So some of our exceptions would be these four right here. Okay, so I've got tin, lead, bismuth, and thallium. Those four exceptions you are going to need to know, and you are going to need to recognize what their charges could be. Okay. Now, if you do notice, they don't have just like 15 charges you have to try to keep in mind. There's only 2 for each one, but they are ones that you do need to have memorized. All right. Now, those act a little bit strange, kind of like a transition metal does, right? When we talk about our transition metals, a lot of times what we recognize is that their charges can change. And it has to do with their d orbital, right? Those electrons that are sitting in the d orbital. When we lose electrons from that d orbital, what we're going to see is that those electrons have different places they can come with. Yes, they always are first lost from their highest energy level, but now instead of just being on that furthest energy level, we've also got some spaces on the lower energy levels. For example, with something like scandium. Scandium has 3 electrons that it added on that 4th energy level, right? Well, it would think that, but remember when you're talking about the d orbital, that electron actually gets added to that 3rd energy level, that extra electron. So we see 4s, and 4s has 2 electrons there, but then we also see a 3d. That 1 electron got added to the energy level below because there was more space there. There was actually enough attractive force to hold that electron in a little bit closer, but not enough attractive force to keep it on that outer ring. Not enough attractive force to keep it on that 4th energy level. And so we see these different charges that happen because these transition metals can lose different amounts of electrons because of how their electron cloud looks. So now that we've got a general idea of what's going on with our bonds, let's actually look at the types of bonds again. So our types of bonds are ionic, covalent, and metallic. Ionic, remember, is a bond between a metal and a nonmetal. And what we see is those electrons are actually being moved from one side to the other. They're going to be moved from one atom closer to the other atom. Does that first atom, does atom 1 lose the electron? No, but it doesn't have as much control. That electron is further to the other side, further to atom 2. And so since it's closer to atom 2, now atom 2 has a more negative charge. And since it's further from atom 1 now has a more positive charge. Now, if I'm talking about covalent, what we see is that's going to form between our nonmetals. We've got nonmetal bonded with another nonmetal. And this is when our electrons are actually going to be shared between one another. So you'll see a carbon bonded to a nitrogen. Those electrons are kind of sitting directly in between them. Right? It's sitting right there in between the carbon and the nitrogen. Metal and metal, though, that's a metallic bond. In metallic bonds, those electrons don't really focus on one atom over another. Instead, they're kind of all over the place. They are equally spread around all of them. And we could see them kind of floating from one side to another. And so we get these areas where we do have very high charge that forms because those electrons can move to one side over the other. And so we get these charges that form. So that's what the second part of what today's lesson actually is over. It's over metallic bonds. So when we're talking about metals, again, remember that metals have a low ionization energy, and that's why they actually easily form ionic bonds. They are going to easily lose their electrons. Okay, so we know that metals easily lose their electrons. So what happens when we get a bunch of metals together? Well, they're going to easily lose their electrons amongst each other. And the simplest kind of idea of thinking about this is thinking about a sea of electrons, where you've got these little islands of metals, and then those electrons are kind of like the sea that's all around them. Okay? And so those delocalized electrons, those electrons that are between them, are going to be freely moving. So they are freely moving around the atom. Oh, sorry, around the metal. Okay. Now the bonding results, so the reason that metallic bond forms is because those electrons are going to be delocalized. And so what that means is those electrons will start to float away from one thing. Well, now we've got a charge that's going to form. And so those metals, positive and negative, you've got a positive charge and a negative charge, you're going to start to attract each other. And so that's what you see. That's how a metallic bond actually forms. And that sea of electrons, those properties that we see, those electrons freely moving amongst all those islands, are what make metals have the properties that they have. So the sea explains why they're good conductors. Well, you need to have that charge for that electron to move, or for that photon to move from one side of a metal to another. So they make fantastic conductors. They also reflect light. Again, kind of the same idea. We've got to have that charge for that reflective surface to actually form. They're malleable and ductile. Why do you think they'd be malleable and ductile? Well, I mean, if you think about it, if those electrons are freely moving around, we've got a lot more space, right, for things to kind of bend. And so since they're going to be more bendable and more able to be stretched into a wire, that's all caused because of our electrons. And generally, they have a very high melting and boiling point. Again, it has to do with those electrons because they're kind of constantly moving around. We've got that kind of resistance to that melting, right? Because there is already a lot of energy going on in there. The exception to that would obviously be mercury. It is obviously a liquid at room temperature, but in general, they do tend to have very high melting points. And in general, we do have a trend that as we go from left to right across the periodic table, we're going to see an increase in those melting points, which would mean we're going to increase in our boiling points as well. And then melting points is actually going to decrease as we move down. Again, we're talking about those electrons, and as we move down, what's changing? Well, what's changing is the size of the atom. The atom's getting larger, and so everything's further away, and since everything's further away, those electrons are more easily able to be taken out. Okay. Well, what happens when I take things and I mix them with a metal? Well, when I take things and I mix them with a metal, a lot of times what I'll form is what's called an alloy. Okay? And we make these alloys because alloys actually start to exhibit different properties. They exhibit the properties of the other things that are a part of the alloy. For example, when we're talking about an alloy, like let's talk about brass or bronze. When we talk about bronze, it was made in the past. Copper is very, very malleable. It's very easy to bend. It's very dentable, I guess. Okay? And back in the Bronze Age, they decided, well, what can we do to fix this, right? Because we've got a lot of copper. We're able to use a lot of copper, and we know that copper is a good metal to work with. It's easy to work with. But it's so easy to work with, it's really hard to make it to where it actually protects us. And so they started trying to, well, what happens if I melt this with this and start mixing things together? And what they found was that when they take that and they mix it with some other stuff, we're actually going to form a alloy that's much, much sturdier than what we would find with typical copper. And so that's what we're actually going to see with these alloys, is that we're starting to get some different properties occurring because there are different things going on inside of that. So let's actually look at that. If I've got a pure metal, this is what a pure metal would look like. Okay, we've got our islands, and those electrons are going to be freely floating around inside between those metals. Now, I've got two different types of alloys that can form. The first type is called an interstitial alloy. Okay? Now, if you notice with an interstitial alloy, we're actually going to have things that actually fit inside of that gap. Okay, the gap between the metals. We've also got a substitutional alloy, and it is exactly what it sounds like. We're actually going to substitute some of that metal out. So what does that actually mean? So interstitial alloys are going to happen when we've got things of different sizes, specifically smaller, that are going to actually fit in between those metals. Okay? And when that happens, one is much smaller, and so it's not actually able to replace the metal, but it can actually fit in between the kind of gaps in between those islands of metals. So that smaller atom becomes trapped between the larger islands, the larger metals. Now, because of this, we actually see a reduction in the space between those molecules. And so since that happens, an example of something that could occur is that the substance would actually become more rigid. Okay? It would become less likely to bend. Iron is actually very, very bendable, right? Well, if I take iron and I mix it with something like carbon, which carbon is smaller, I get steel. Well, steel is much more sturdy. That's why we actually make buildings and stuff out of steel. It's sturdy. It's rigid. It doesn't bend. It doesn't tear as easily. Okay? Substitutional alloys, on the other hand, again, we're kind of looking at the mixing in a metal with something else. And in this case, we're actually going to mix in another metal. And what happens is that metal is about the same size, and so that metal will actually take and replace one of the other metals. Now, when that happens, we start to get some of the different properties of that. So, for example, some things don't corrode as easily as things like copper, right? If you leave copper out in the weather for any short period of time in the grand scheme of things, even a week, it'll start to turn green. Okay, it's why the Statue of Liberty is actually green. We could clean it off, and it would be that bronze, that kind of goldish, rustish red color that you typically think of with copper, but we don't do that. But if I take and I add something else to it, if I add some tin to the copper, I get bronze. Well, bronze is very much less likely to corrode. It's like I increased strength, and we're actually going to be changing our conductivity. It's actually less conductive now. So what we're seeing is that we can actually change or alter the properties of a metal by adding in something else. So that's a little bit about our types of bonds that we have, why those bonds form, and then what actually a metallic bond is and how it occurs. Hopefully you understand it now. If you have any questions, please don't hesitate to reach out to us. And it was great talking with y'all. Hope y'all have a great rest of the day. Bye, y'all.